Okay, welcome. I was inspired to this video by two videos Dave Jones posted on YouTube about powering LCD displays in the right way. The concept of the, in quotation marks, magic voltage doubling is well known in audio electronics since decades. It's called single supply push-pull amplification or bridge rectifier or rectifier.
A full bridge rectifier.
A bridge amplifier. With this technique of working with differential potentials, you can achieve more voltage on a load, aka a speaker, than your power supply can deliver. In theory, you can double the voltage, and this is often used in car audio with only 12-volt battery voltage or mobile devices, and there are many dedicated ICs like the TDA7266. Let's have a short look to the block diagram of the TDA7266, an audio amplifier, a single supply audio amplifier, and as you can see, the speaker is connected directly to two op amps, and one op amp is in non-inverting configuration and the other op amp is in inverting configuration. And as you can see, the out minus terminal or the negative terminal has no relationship to ground. It goes to the output of the inverting op amp. We will measure this soon. The Vref is basically supply voltage, the half of the supply voltage to bias the op amps. And to understand this configuration, we need a closer look to the basics of switching of potentials. Let's start with this very simple configuration: 5-volt power supply, 2 NOT gates, and a load resistor with 1 kilo ohm. I start the simulation, and as you can see, if I change the switch, yes, 5 volt, 0 volt, 5 volt, OC shows 5 volt. Switch to ground, ground, 5 volt, ground, 0 volt. Very simple. Let's have a closer look to the current flow. The current flow in this simple arrangement is very easy to understand. So let's assume the switch is connected to ground. So we have 0 volts on the output, inverted 5 volts on this output, 0 volts. So we have no voltage drop over this resistor, no current can flow, 0 amps or milliamps. Now let's assume the switch is connected to 5 volts. We have 5 volts on the input of this NOT gate. The output is 0 volts, inverted 5 volts, and now current can flow. We get 5 milliamps because according to Ohm's law, 5 milliamps times 1 kilo ohm is 5 volt voltage drop over this resistor. The current can flow to the negative terminal of the power supply. Each NOT gate has its own power supply, and in reality current comes from this power supply terminal of the IC, connected to, well, the power supply. Now I changed the circuit a little bit. I connected the bottom terminal of the resistor to the output of the first NOT gate, and I draw the first NOT gate a little bit lower than the second NOT gate, and let's start the simulation. The switch S1 is connected to 5 volts, so the first NOT gate has 5 volts, and the resistor has a voltage drop of plus 5 volts. Let's activate the switch or push the switch and connect it to ground, and magically we see minus 5 volts over the resistor. OC shows -5 volts. Switch, +5 volt. Switch, -5 volts. Switch, +5 volts. Switch, 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 switch. I stop the simulation, and you can see on the OSI the resistor is connected between +-5 volts or 10 volts peak to peak. I guess we need further investigations. First, let us draw the power supply rail of each NOT gate. It's very useful to understand what's going on in this circuit. Okay, let's assume the switch connects the first NOT gate to 5 volts. So the output is 0 volts. 0 volts is the input of the second NOT gate, and the output of the second NOT gate is 5 volts. The voltage drop over the resistor R1 is 5 volts, and we have a current of 5 milliamps. The return path of the current is directly straight into the first NOT gate. The NOT gate sinks the 5 milliamps and over this path back to the power supply. Easy. Like before, we first draw the power supply of the two NOT gates. 5 volt, 0 volt or ground. Now let's assume the switch connects the input of our first NOT gate to 0 volts or ground. This will lead to an output voltage of 5 volts, and these 5 volts are the input voltage of the second NOT gate, and we get 0 volts. Now our resistor is connected with the bottom terminal or the lower terminal to 5 volts, and this will produce a voltage drop of 5 volts in this direction. Current can flow from the bottom side of the resistor through the resistor straight into the input of the second NOT gate, to the ground terminal, back to the power supply. Our NOT gate sinks 5 milliamps. We didn't change anything at the multimeter. Let's assume this is the red terminal and this is the black terminal of the multimeter. So current can flow into the black or negative terminal of the multimeter back to the second NOT gate, and this is a very small current because of 10 megohm input current, but this is the direction. And when current goes into the black terminal, this will produce a minus sign in the display of the multimeter, likewise on the OSC. So when we switch the input voltage on the first NOT gate, we see something like this: plus 5 volt, minus 5 volt, plus 5 volt, minus 5 volts, around 0 volts, with a peak voltage of 10 volts, plus, minus 5 volts, 10 volts, peak to peak. If we will draw an arrow with plus on the top and minus on the bottom, we must write a negative sign, because our minus terminal, or the bottom of the arrow, has plus 5 volt. Interestingly, the arrangement or the concept from the previous example does not only work with digital signals but also with analog signals. I changed the two NOT gates to two op amps in inverting configuration. 10K, 10K amplification is -1. The same below, 10K, 10K amplification -1, and the output of the first op amp is the input of the second op amp. I have a single voltage supply with 12 volts, and with this 10K resistors R6 and R7 I bias the op amps. The load, maybe a speaker, is connected between the output of the two op amps, and the oscilloscope is parallel to the load. I feed the circuit with a sine wave of 1 kHz and 1 volt peak, and now let's discover what we will get. Assume I have a sine wave with 1 volt peak or 2 volt peak to peak. If the input falls, the output of the first op amp rises. This is the input signal of the second op amp. The potential of the second op amp falls, and the oscilloscope measures the voltage between these two. I have 1 volt peak, I have 1 volt peak in the other direction, and on the oscilloscope the oscilloscope measures the difference between these two outputs. We will get a sine wave, or the half of a sine wave, with 2 volts peak. Now assume the output is rising over 0 volts. The output of the first op amp falls, the output of the second op amp rises, and now we measure -2 volts peak. Remember, the oscilloscope measures the difference between the signals, and now the positive terminal of the oscilloscope is negative against the negative terminal, and so we have -2 volts peak to peak voltage in this direction, the difference. Okay, let's look whether we are right. I will start the simulation. 1 kHz, 1 volt peaks. Okay, that looks good. I adjust the scale, and we see 1 volt peak and 2 volt peak, 2 volt minus, 4 volt peak to peak. Great. Now we can add amplification at the input of our circuit. Let's do 5. 10K divided by 2K is an amplification factor of -5. Simulate. Okay. Now we have to adjust the volts per division, and we get plus minus 10 volts peaks, or plus minus 10 volt peak minus 10 volt peaks, or plus minus 20 volts, with a power supply of only 12 volts. This is exactly what the manufacturer of the TDA7266 did, but he chose an arrangement of a non-inverting op amp and an inverting op amp. That's so critical because we only need the original signal and an inverted version of the signal. but as mentioned before, my circuit fits better to the previous example. Before we will do some real measurements, a short annotation. Interestingly, the oscilloscope from the simulation software is not ground referenced on the negative terminal. But in real life, the negative terminal of the oscilloscope is ground referenced. And that's a problem, because we will shorten the output to ground. So in real life we need a isolation transformer. 230 volts to 230 volts. Let's do it. Okay, welcome to my lab bench, and let's do them quick measurements with this cheap audio amplifier with the TDA7266. This device can be powered up directly from 12 volts, so no need to work with dangerous voltages. You see the isolation transformer for the oscilloscope, and the first thing I will show you is that the negative terminal of the speaker output has no continuity to ground, to system ground. I use the system ground from, or the ground from the RCA checks on the input, and you will see continuity. Now I go to the negative terminal of the speaker out and no continuity. Isolated from ground, as shown before in the theory part of this video. Let's power up this device with 12 volts. We have an input signal, and the input signal is about 1 volt peak to peak on the signal generator, and 7 kilohertz. 7 kilohertz because of the frequency response of the device, of the amplifier, and yeah, the equalizer in the front fits good. Let's show what we get on the oscilloscope. Magically 22 volts peak to peak, not exactly 24, but 22 volts. Magic voltage doubling. 22 volts because of the losses of the legendary
Full Bridge Rectifier.
Okay, I hope you enjoyed the video. Thank you.